So we're going to continue talking about PDEs, time, space, stepping schemes. Okay? So let's never forget what we're really doing. What we're ultimately doing in all of this is just setting up an iteration. I made this comment at the beginning of class, right? Your computer loves to iterate. That's all you're ever going to have it do for you. Everything we're doing for solving these equations is all about setting up an iteration equation where you just say, go. And it just keeps computing. Okay? Keep that in mind. So one of the things that we talked about early in the class, first 2-3 lectures, right, was when you set up an iteration scheme for differential equation, one of the things you always worry about is, well, can you just set up any iteration scheme, set it going forward, and it's just going to work? There's a big issue about the idea of stability and accuracy. Those are the two things we always talked about. So now we have to kind of hit these themes again in the context of both space and time. Right? You can't just do whatever you want. There's some restrictions. Okay? All right. I know you think you can do whatever you want. It's your code. So you can, in some sense, do whatever you want. It's just that if you want to, there's this other question you have to ask is, okay, can I get the right answer and do whatever I want? And then the answer is no. Okay? So we want to try to figure out what are constraints in these problems. So to illustrate it, what I thought we would do is study what's called the one-way wave equation. It's called the one-way wave equation because there's a wave and it goes one way. That's the solution to this thing. Okay? I can also write this in a little nicer shorthand notation like this. Those are partial derivatives. So space, time. This is one of a classic PDE. The heat equation, the one-way wave equation, they're the simplest PDEs possible. And I can write down the solution explicitly for you for this. But what we want to do is say, okay, if I were to go solve this on the computer, how would I think about doing it? And we already have all the tools that we need to do it. But I want to show you sort of the variety of techniques you can be applied just to this simple equation itself. Okay? And introduce to you a very important parameter in the problem. Okay. So first of all, we have discretization in space. So let's start off with that. I would solve this thing on some domain, right? And I'm going to chop it all up to a bunch of points. So this is my x domain, and I'm going to solve this in time forward. And here's my solution u. So it's like a three-dimensional picture. We're going to start at some time, march it forward. But what we know about derivatives is, if I want to calculate the derivative at a certain spot here, I can just go to my second-order difference formulas, for instance. And that just tells me I just use two neighbors to calculate the derivative. It's a slope formula, rise over run. Very simple. So any point here, the unth point relies on un plus 1 and un minus 1. Okay? So when we do this simple discretization, we find that, okay, so this u of t equals cux is going to turn into, at the nth point, I'm going to have u of n t is equal to c. The derivatives, point in front minus the point behind minus 2 delta x. Rise over run. That's a slope formula. Okay? That's all we're going to do. So notice what we can do here. Say, okay, now what I have is a set of differential equations. Before we were just saying, let's just throw that into OD45. But now we're going to step back a bit and talk a little bit about this guy here, which is we want to say, okay, how do we normally do a discretization of time? Well, we talked about that first couple lectures, the first lecture of class. And let's now discretize this the same way we discretize this. Let's use a slope formula. So this is, in fact, rise over run also. And what I'm going to do is do the following rise over run. This here I'm going to approximate with u of n. Let me write it down. There's the slope formula. Rise over run. This m represents the time at m plus 1, and this is time at m. So in other words, when I start thinking about u of n m, this is the solution at the nth point and at the tth time. Okay? So I'm going to march forward. M is my discretization of time. M equals 0 is my time equals 0. And then M equals 1, 2, 3, and so forth. And that's just a slope formula. Same thing I did before. Is equal to C un plus 1 minus un minus 1. These are now at, I'm going to evaluate these at time m to delta x. Everything's discretized now. Everything lives on a grid. And my future is right there. That's the m plus 1. I have, let's say, the solution at time m, and I want to determine it in the future. So I can rearrange things here to get the following. Oops. That doesn't look like a u to me, but let's try this again. Okay. U of n m plus 1 is equal to u of n m plus c delta t over delta x, and there's a factor of 1/2 u n plus 1 m minus u n minus 1 m. Here is our iteration scheme. Okay? My solution in the future is what it is right now. Right? So the idea is to take small steps forward. So my future hopefully doesn't change very much from the present, or it should change slowly from the present. Every time you step something forward, it's going to change by this much. Future is what it is now, plus a little bit of something, and here's my something. And my little bit of something depends upon my neighbors. Okay? So in this scheme here, if I want to go forward into the future, a delta t, these 3 points here determine my point in the future. So I use these 3 points to get me my future point. This is my stencil. It's a 3-point stencil. 3 points determine my future. Okay? So that's it. I set up an algorithm, and what I do is say I want to update my whole solution in the future. And I just go to a point and say take the 3 points behind it that are time m, add them up in the right way. That gives me my future solution. And once I get this row filled in, go to the next row. So this is delta t into the future, 2 delta t into the future, 3 delta t into the future. I just iterate. That's it. Now there's an important quantity here, this thing here. And I'm going to define this scheme here. So I'm going to actually, well, I'm going to do some fancy board work today maybe. So let's come over here. I'm going to define this quantity here called lambda. It's c delta t over delta x. This is called the CFL number. It was invented in the Canadian Football League, which I'm sure you all know. Courant, Friedrichs, Louis. So these guys in the early days of computing started looking at these iteration schemes, and there's this important number here, lambda. And the stability of any of these schemes is going to be related to the CFL number. So you often hear about the CFL condition. What the CFL condition is basically saying when I construct an iteration scheme, when is it stable? And it turns out a lot of schemes are only stable under certain restrictions on lambda. Okay? So that means you better not step outside of that CFL condition, or otherwise you're going to go unstable in the scheme. What does unstable mean? You start iterating along and things blow up. Okay? And we're going to illustrate it in class right there on my computer. I'm going to blow up some code on you. Okay? So you'll see what it means to violate the CFL. Okay? The nice thing about violating a CFL condition is I always tell this to people because a lot of times people worry, is my scheme stable, is it not stable? Almost all the time, if it's unstable, it will let you know. Because you'll be marching along, all of a sudden your solution's NaN. And it just blew up. And you go, oh, whoa, that's some cool physics. No, it's not physics. It's unstable schemes. Okay? So you typically don't have to worry about working so hard to see what's my CFL number. You violate it, your code will say, I'm not going to work.